Afternoon, everyone. We are very pleased to be here today. First of all, let us introduce ourselves. We are Group 2, especially my name is Nayda Mawaddah Nur, and now I'm here with my team, Komang, Vini, Syahrani, Nabila Zahrotunisa, and Shaffa, Athiyyah, Salsabila. And today we would like to explain to you guys about graph of the effects of ZnO, or we can call it as a zinc oxide loading on band gap energy. And let's go back to the topic.
So let me explain. My name is Komang Syahrani, and I'll explain for this graph. The graph illustrates the variation in the band gap energy, or EG, of a materials as a function of ZnO, or zinc oxide loading percentage, ranging from 0.5% to pure ZnO. The vertical axis represents the band gap energy in electron volts, or EV, while the horizontal axis shows the ZnO loading percentage. The general trend indicates a gradual decrease in band gap energy with the increase in ZnO content.
Let me introduce myself. My name is Nabila Zahrotunisa. So at 0.5% ZnO loading, the material exhibits a relatively high band gap of approximately 3.26 EV. This value steadily drops as the ZnO loading increases. By the time the loading reaches 2.0%, the band gap reduces to about 3.18 EV. Finally, the band gap reaches its lowest point, roughly 3.14 EV for the pure ZnO sample. This downward trend suggests a correlation between ZnO concentration and the material's electronic structure.
And then, one possible explanation for this decrease lies in the quantum confinement effect and the interaction between the zinc oxide nanoparticles and the Mohs metric. As more zinc oxide is incorporated, it may introduce defect states or change the local electronic environment, resulting in a narrowing of the band gap. According to a study published in the Journal of Material Science, such modifications in the band structure are common when semiconductor oxides are doped or composite with other materials.
Particle terms, the tanning of the band gap through ZnO loading can be highly beneficial. A lower band gap means the material can absorb a broader range of light wavelengths, especially in the visible spectrum. This property is particularly useful in applications such as photocatalyst, solar cells sensor. For instance, ZnO-based photocatalysts with narrow band gaps can perform more efficiently under sunlight, enhancing the degradation of pollutants or production of hydrogen via water splitting.
Then, furthermore, the ability to engineer the band gap through controlled ZnO loading provides material scientists and engineers with a strategic tool for optimizing the performance of optoelectronic devices. Research in applied surface science has shown that doping and surface modification are widely used to alter the band gap of ZnO to meet specific application needs, such as UV detectors of transparent conduction film.
Next, from an academic perspective, this graph serves as a clear demonstration of how compositional variation can influence fundamental electronic properties. The consistent trend suggests the material system is stable under the applied modification and that ZnO is effectively integrated without phase separation or anomalous behavior.
Okay, guys, that's it, the explanation about the graph of the effects of ZnO or zinc oxide loading on band gap energy. And now we can go to the conclusion. Okay, overall, the graph shows that increasing the zinc oxide loading percentage leads to a steady decrease in band gap energy from about 3.26 electron volts to 3.14 electron volts. This trend not only confirms the impact of zinc oxide on the material's optical properties, but also opens door for tailored design in advanced material systems.
Such insights are critical for the continued development of efficient, cost-effective, and versatile semiconductor-based technologies.
Okay, guys, that's it. Our present of the graphs about the effects of ZnO or zinc oxide loading on band gap energy. Thank you for your attention, and thank you, guys. Bye bye.